Welcome to the deep dive. Today we're taking on a concept so basic, so woven into the fabric of our lives that we rarely stop to question it. Time. We measure it, we worry about running out of it, and we depend on its steady forward march.
We do, but it's an illusion.
A powerful one.
Yeah.
But when you look at the deepest levels of physics, at the very foundations of reality, that steady universal tick-tock it collapses. Our sources today take us on a pretty dizzying journey, pitting Einstein's theory of gravity and space-time general relativity against the laws of the very small quantum mechanics.
And it's a genuine conflict. There's no easy resolution.
Right. So our mission today is to unpack that catastrophic conflict between these two pillars of modern science, a conflict known formally as the problem of time. We need to understand why our experience of universal flowing time is, well, overwhelmingly considered by leading physicists to be nothing more than an emergent, convenient illusion.
That is the ultimate conclusion. And it requires a radical shift in perspective, a really radical one. If you think about the two theories, the clash is immediate and violent. Quantum mechanics fundamentally requires time to be an absolute external metronome, the fixed stage upon which all the strange quantum interactions occur.
Okay, so it's the backdrop.
It's the backdrop, yeah. But general relativity says definitively that time is dynamic, relative, and merely an arbitrary coordinate label. It's part of the action, not the fixed background. So we have to discard the comfortable Newtonian idea of a universal big clock ticking outside of the cosmos. GR showed us that space and time are fundamentally intertwined with matter and energy. And if we want a quantum theory of gravity, we must accept that the universal clock is gone for good.
Okay, so let's unpack this by starting where intuition was born. The classical world. Let's remember the comfort of Newtonian absolute time.
Yeah, Newtonian physics provided this incredibly elegant framework. Time, symbolized by the letter T, was considered an external, continuous, and absolute parameter. It flowed equably, as he put it, without relation to anything external, regardless of whether a planet moved or a star burned out. It was just there, extraneous to the physical system itself.
And crucially, it was perfect for simplifying equations. We could define the state of a system, say, the position of a particle, alpha, as a function of this perfect time, alpha of t.
Yes, but this was always a convenient fiction. I mean, even the earliest supposedly objective measurements were relational. Think of Galileo timing the chandelier swing in the cathedral. What was he really doing?
He was using his pulse, right?
Exactly. He was measuring the relative evolution, the swing of the pendulum compared to the beat of his own pulse.
So he wasn't connecting to some cosmic master clock. He was just correlating two observables, pendulum swing versus pulse count.
That's all you can ever do. But Newton formalized the convenient assumption that any device we use, a sand timer, a metronome, a cesium clock, moves proportionally to that invisible, true, universal time, t. We write all our physics in terms of t because it simplifies the math, but empirically, all we ever measure is A relative to B, or alpha of beta. This fiction works beautifully until you start dealing with speeds near light.
And it collapses completely when you deal with gravity.
Complete.
That collapse is the jump to general relativity, and it's a massive conceptual leap, greater even than the move to special relativity. So GR eliminates absolute time entirely. How does it, enforce this removal?
It does it by treating all coordinates, t, x, y, z, as purely arbitrary labels. If you write down Einstein's field equations, the coordinate time, t, has no intrinsic physical meaning. It's a mathematical tool. It's like using latitude and longitude on a map. The map itself is the physical reality, not the lines you drew on it.
So if I pick a different set of coordinates, a different way of drawing the lines, the physics has to stay the same.
Precisely. The measurable physical content lies not in the coordinate values, but in the invariant relationships between observables, the curvature of space-time, the distance between two objects, or the frequency ratio of light emitted from different locations. Physical clocks, however, they do measure something real. Proper time, which we call S. This is the time measured along a specific path or world line taken by that physical object. Proper time is an invariant measure of the space-time interval between two events. It is physical, the coordinate time is arbitrary. The universal background clock is officially banished.
Okay, so this means if I'm standing still on Earth and you're flying by in a fast rocket, we can agree on the physical relationship between us. But our proper times, our S1 and S2, are fundamentally different, and the coordinate time we use to describe that relationship is just a shared bookkeeping system.
That's it. And because the coordinate choice is so free subject to what we call diffeomorphism, or general changes of coordinates, we arrive at this wonderful concept of many-fingered time.
I love that phrase. It perfectly captures the messy reality.
It does. In GR, when we try to evolve the universe forward, we are essentially slicing the four-dimensional space-time into a series of three-dimensional space-like hypersurfaces. We call this a foliation. But because there are infinite ways to choose these slices, infinite ways to define simultaneity, you get infinite possible time functions. Time is not one universal tick. It's many different arbitrary fingers pointing in different directions.
And this arbitrariness, this dynamical nature of time evolution, is literally written into the mathematics of the metric, isn't it? Tell us about the lapse and shift functions. They are key to understanding the geometry of time evolution.
They are absolutely crucial. When physicists perform what's called the 3+1 split, separating the gravitational field into spatial components and temporal components, two fundamental geometric objects emerge: the lapse function n and the shift vector n with an arrow over it. The lapse function n relates the proper time separation between two adjacent hypersurfaces. Conceptually, n tells you how much coordinate time t corresponds to actual measured proper time s at a given point. If you change n, you change your rate of time evolution.
And that function n is dynamic. It's not fixed.
Precisely. And the shift vector specifies the spatial displacement between slices. It tells you how the spatial coordinates shift as you move forward in time. Both n and the shift vector are components of the space-time metric itself. They are fields that obey their own dynamical equations.
So the implication here is profound. Time evolution parameters are not external. They are geometric objects embedded in the theory. Unlike Newtonian physics, where time was this rigid background, here, the components that dictate how we move through time are fully dynamic, flexible, and utterly dependent on our arbitrary choice of coordinate slicing. They are part of the four-dimensional space fabric that we're trying to quantize.
And that is the problem.
Yeah.
Because they are dynamic variables, they are the very things that must be quantized, which leads us directly to the crisis.
So we've established that general relativity turns time into a rubber ruler and an arbitrary coordinate. Now, we try to force this rubber ruler into the rigid framework of quantum mechanics. This is where we face the crisis of unification.
This is truly where the foundations of our two greatest theories clash. The standard Copenhagen interpretation of QM is predicated on the existence of a fixed external time t where we perform measurements. Operators are defined at a given time.
Right. It needs that external clock.
It's built on it. GR, however, rests on diff m invariance under spacetime diffeomorphisms. This is not just changing labels. It means that if you physically move every point in spacetime to a different location, the underlying physics remains identical. This high degree of coordinate freedom means that individual space and time points lose all ontological significance. There is no background structure left and nowhere to bolt down that external clock QM requires.
So if we try to apply the standard recipe for quantizing fields, the canonical quantization procedure, to general relativity, we immediately encounter the frozen formalism problem. What does the math spit out?
The canonical procedure, perfected by Dirac, is used when a theory, like GR, has intrinsic constraints due to its coordinate freedom. We take the classical constraints of GR, the Hamiltonian constraint and the momentum constraints, and promote them to quantum operators that must annihilate the quantum state psi.
Wait, what does annihilate mean here?
It means that when the operator acts on the state, the result is zero. The supermomentum constraint ensures that psi is independent of spatial coordinate changes. Fine. But the key, the real kicker, is the super-Hamiltonian constraint, which forces the quantum state psi to satisfy the Wheeler-DeWitt equation, h perp psi equals 0.
Now, let's be very clear about the physics of that zero. The Hamiltonian operator, h perp, is traditionally the generator of evolution in time. It's what makes things change. If the quantum state, the wave functional psi of the entire universe, is annihilated by the Hamiltonian, what does that zero physically imply?
It implies that the state has no evolution with respect to any external time parameter. The universe's wave functional is defined over the space of all possible three-dimensional spatial geometries. This is called superspace. Since the Hamiltonian is the operator that moves you between these slices and it annihilates the state itself is independent of the slicing.
So, it's frozen.
It's frozen. The universe is described by a stationary frozen wave functional. Time disappears entirely. It describes a static state of being, a correlation across superspace, not a dynamic process of becoming. Only the three-metric space remains as a fundamental object.
This is the ultimate conceptual nightmare. I mean, if the entire cosmos is described by the Wheeler-DeWitt equation and the state is frozen, then the entire sweep of cosmic history, the Big Bang, the expansion, the rise of civilization, our deep dive right now, is mathematically just one timeless structure.
It is a structure where every event, every birth, every death, every time you missed a flight or, that awkward moment you waved back at someone who wasn't waving at you, it all exists simultaneously within a single static quantum object.
We are all, mathematically speaking, existential popsicles frozen into the geometry of a timeless statue.
That's a perfect way to put it. We're just part of a timeless dream. The challenge for physicists then becomes, how do we extract the perception of flow from a system that is fundamentally designed to be motionless?
That freezing is a consequence of trying to quantize space-time itself. But even if we restrict ourselves to standard, non-gravitational quantum mechanics, the concept of time is still fundamentally shaky due to the imperfection of clocks.
Right. This is a separate but equally critical component of the problem of time. It reveals that the very act of measuring time accurately is incompatible with fundamental QM principles.
How so?
Well, a perfect clock, an idealized physical system that measures time, let's call it operator T that accurately, would have to satisfy the canonical commutation relation. The commutator of T that and H hat equals I bar. That relation, linking time and energy operators, is what allows us to define time as the conjugate variable to energy.
But what physical restriction does that commutation relation violate? There's a catch.
There is. A big one. Systems satisfying that relation must have energy spectra that span the entire real line, from minus infinity to plus infinity. This flatly contradicts the fundamental physical requirement that all physically realized systems must have energy that is bounded below. They must have a lowest energy state or positive energy. If energy could go to negative infinity, the universe would collapse instantly.
So because the universe requires positive energy, we cannot build a perfect clock that satisfies the standard quantum mechanical definition of time.
Exactly. Any physical clock is necessarily imperfect. The mathematics proves that any realized clock, no matter how precise, must have a small, non-zero probability of measuring time running backwards relative to abstract Newtonian time. It's an unavoidable effect rooted in the positive energy requirement of reality.
That's a dark thought. So you can never trust a clock entirely because at a fundamental level, it's secretly trying to reverse time.
Yeah.
Unfortunately, the effect is only measurable at the Planck scale. So my retirement plan is safe, but it's mathematically unreliable.
Your retirement plan is safe. But yes, the unreliability is inherent.
If the universe is frozen by the Wheeler-DeWitt equation and external time is fundamentally unreliable, we have to invent a new way to describe dynamics that doesn't reference an external t. This is the foundation of timeless mechanics.
This new mechanics has to be relational, focusing purely on correlation. This requires a process that we sometimes call Hamiltonian reduction, where we eliminate the coordinate time t by choosing one of the system's physical observables to act as the internal clock.
So instead of asking how does x change over time t, we ask how does x change relative to y, where y is another measurable dynamic variable in the system.
Correct. We focus on partial observables quantities you can measure simultaneously. Let's stick with the simple pendulum and clock example, but elevate the concept. The elongation of the pendulum alpha and the clock reading beta are our partial observables. A simultaneous measurement is an event, a point, alpha beta, that exists in a high-dimensional configuration space, or event space. Motion, or dynamics, is captured not by two separate time-dependent equations, but by a single relation or correlation that defines a path within the event space. F of alpha and beta equals 0. For our simple pendulum, the path looks like a sinusoidal curve. Alpha minus a sine omega beta plus phi equals 0.
This means the external clock tet is eliminated entirely. Dynamics is simply navigating the correlated pathways within configuration space, and one observable, beta, acts as the reference against which the evolution of alpha is measured.
Yes, beta is the internal clock. This relational structure is powerful because it is physically consistent with general relativity, where only relative quantities have physical content. And importantly, this structure is general enough to accommodate Newtonian physics too. You simply designate one partial observable tet as the preferred non-relativistic time variable.
This philosophy, often championed by Julian Barber, is summed up by the Latin phrase, tempus nihil est time is nothing. It posits that being is primary, the single instantaneous configuration of the universe, and becoming, or history, is secondary or apparent.
That's the core of the school of thought. If the universe is fundamentally a single timeless snapshot, often called Platonia, then we must explain the semblance of dynamics. How does the appearance of flow emerge from stillness?
And this leads us directly to Rickard's theory. If the universe is just one frozen wave functional, how do we explain memory, or the perception of past events?
Records theory suggests that the semblance of dynamics is abstracted from records, which are specific information containing subconfigurations of that single instant. A record is a small, localized piece of the universe that, due to its structure, contains information that can be read as a history.
Give me an example.
Okay, a physical example, a fossil. The fossil itself is just a configuration of minerals that exists now. But its structure, the imprint of a bone, is a record that an observer can interpret as a sequential history. The fossil, or a cosmic background radiation map, or a light-year-long track of an alpha particle all exist at the same moment in the timeless description. They are localized in both space and configuration space.
So the past isn't a place we visited. It's a correlation encoded in the structure of the present.
Exactly. The fundamental question shifts. We stop asking questions of becoming. What is the probability of P2 happening at time T2, given P1 at T1? Instead, we analyze a temporal questions of conditioned being.
Okay, what does that mean?
We ask, what is the probability of having property P2, given that we have property P1, within the context of this single instantaneous cosmic state? The records are the internal mechanism that establishes the correlations we interpret as cause and effect, or past and future. It's a remarkably beautiful, albeit radical philosophical position.
The implication for us as observers is rather dark then. If we're simply interpreting correlations within a frozen instant, our perception of time as a directional flow might just be an evolved cognitive convenience, rather than a fundamental truth about reality.
It very well could be.
So, time is banished, replaced by timeless correlation. But we still experience change. To bridge this huge conceptual gap and recover the world of yesterday and tomorrow, physicists turn to approximations. We need to find a semi-classical regime where time emerges.
Yes, the full quantum gravity description, the Wheeler-DeWitt equation, must allow for a limit where one specific observable can be extracted and act as the standard non-relativistic time t.
How was that done?
The technique used is the WKB approximation, which is common in quantum mechanics. Think of it as the short wavelength limit, or the equivalent of the Born-Oppenheimer approximation in chemistry, where you separate variables based on their relative mass or speed.
And how does that apply to the whole universe?
Well, the Wheeler-DeWitt equation is second order in derivatives, reflecting its gravitational origins. The WKB method allows us to treat the gravitational degrees of freedom. The three-metric G is evolving very slowly, and the matter fields, the quantum fields, as evolving quickly.
Okay, slow gravity, fast matter.
Right. By applying WKB, we essentially factor the second-order Wheeler-DeWitt equation into a first-order functional equation. If we carefully isolate the part of the gravitational field G that acts as the slow variable, the emergent size or scale factor of the universe, we can identify that variable as our emergent time t.
And what does that remaining first-order equation look like?
It looks exactly like the familiar time-dependent Schrödinger equation. I bar partial psi by partial t equals h true psi. Crucially, the time variable t is extracted from the gravitational variables, and the remaining Wheeler-DeWitt structure becomes the true Hamiltonian that governs the evolution of the matter fields.
This is a tremendous result. The time we use in all of quantum mechanics isn't an absolute external stage. It's an emergent property extracted from the very geometry of the universe itself.
Yes. The Schrödinger equation is derived, not postulated in this regime. However, this recovery isn't perfect, and it revives a major quantum problem.
The Schrödinger cat problem.
Precisely. A single WKB solution for the quantum state psi still corresponds mathematically to a superposition of multiple classical histories simultaneously. In quantum cosmology, for instance, the solution derived might describe a universe that is both expanding and contracting, or perhaps one with different cosmological constants, all coexisting in the superposition. We don't see that. We see a single, definite classical history.
So the next step is to introduce the mechanism that kills the superposition and selects the single classical history we observe. That mechanism is decoherence.
Right. Decoherence is usually defined as the irreversible emergence of classical properties caused by the unavoidable interaction of a system with its environment, meaning all the degrees of freedom we aren't explicitly tracking. The environment constantly measures the system, forcing the superposition to collapse into a classical mixture.
Okay, but in the context of quantum gravity and the relational nature of time, our sources mention a more fundamental process: fundamental decoherence.
That's right. What's the difference? Environmental decoherence is contingent on outside interaction. Fundamental decoherence is inherent in the structure of the theory itself. Because quantum gravity demands a relational time structure, the mere act of defining time using internal clock variables intrinsically modifies the evolution of the system.
So just by having a clock, you get decoherence.
In a sense, yes. This modification dictates that pure quantum states must evolve irreversibly into mixed states. The evolution is described by a non-unitary equation, often a Lindblad-type equation, which is used generally to describe open quantum systems losing coherence.
And this loss of coherence, this fundamental messiness, is where the arrow of time is born.
It's the source. For this Lindblad-type evolution to be physically acceptable, specifically to maintain the fundamental property that probability never exceeds 1, the equation contains a coefficient sigma of t, which must be positive.
A positive coefficient for decoherence means what, intuitively?
It means that the spread of the probability distribution for the internal clock variable must increase over time. Things must spread out. Order must give way to disorder. This positivity requirement, sigma of tet being greater than 0, mathematically enforces irreversibility. It forces the evolution to move toward increasing entropy and loss of information.
So the only reason we move forward is because the universe is fundamentally messy. Order decreases and decoherence reigns. The arrow of time is really just the universe giving up on perfection.
A rather dark but accurate assessment. Our sources confirm this decoherence effect is incredibly small, proportional to the Planck time, making it undetectable in ordinary settings.
But if we can detect it, it would be definitive proof that time is emergent.
Absolutely. The search for this inherent decoherence is one of the most exciting new avenues for experimental quantum gravity. We need to look at macroscopic quantum systems, like giant Bose-Einstein condensates. In these systems, the decoherence rate scales rapidly. The energy spread can go as the number of atoms squared. If we can create condensates large enough, with sufficient energy spread, we might just be able to measure that tiny inherent messiness that validates the idea that time is born from fundamental disorder.
We shift now to a realm where space-time geometry meets quantum information theory, a field that has offered some of the most profound conceptual links between space, time, and correlation, the ER-EPR conjecture.
This conjecture, that entanglement is equivalent to a geometric connection, or specifically that an Einstein-Rosen bridge is the geometric manifestation of an Einstein-Podolsky-Rosen pair, is astonishing. Both QM via entanglement and GR via wormholes violate local intuition, but they uphold locality because neither allows faster than light signals.
Let's contextualize this with the geometric object involved, the eternal black hole. How is this specific solution to GR described quantum mechanically?
Okay, so the maximal extension of the ADS-Schwarzschild black hole solution in GR describes a pair of black holes connected by an interior wormhole, an Einstein-Rosen bridge. The quantum description of this system is the thermofield double state.
And what is that?
This specific quantum state is highly relevant because it describes two identical quantum field theories, call them left and right sectors, that are maximally entangled but non-interacting. Crucially, while the overall state is pure, if an observer only accesses one side, say, the left, the quantum fields on that side appear to be in a thermal or hot mixed state. This is why black holes look thermal.
So the black hole, which appears static and eternal to the outside observer, is fundamentally a manifestation of maximum entanglement between two non-interacting worlds.
Precisely. And the geometric manifestation of that maximal entanglement is the Einstein-Rosen bridge connecting the two black hole interiors. The ER-EKR conjecture is not just an analogy, it states that entanglement is the geometry.
So if I have two entangled particles, the correlation between them is, on some fundamental level, a microscopic wormhole. That's staggering. How specific is this correspondence?
It's incredibly specific. The geometry of the ER bridge is determined by the specific quantum entangled state. If you change the state, for instance, by adding particles, the entanglement structure changes, and this is reflected in a corresponding geometric change in the configuration of the wormhole. It connects the deepest parts of quantum information, like the size and quality of entanglement entropy, to fundamental space-time concepts like connectivity and curvature.
It's vital to reiterate the limitation here.
Mm.
Although there is a geometric connection, this wormhole is not traversable in a useful way.
Absolutely not. The sources emphasize that the ER bridge does not imply causal contact. You cannot use the wormhole to transmit information from the left exterior to the right exterior faster than light. The wormhole closes faster than a signal could cross it. Physics remains stubbornly local.
Let's focus on the temporal element. The sources mention the growing bridge. If the eternal black hole is, by definition, static and non-evolving from the exterior perspective, the density matrix of each side is constant, how does temporal dependence show up?
The black hole's exterior is static, but the interior geometry is profoundly dynamic. The entanglement between the left and right degrees of freedom, which defines the bridge, is tied directly to the interior geometry.
Okay.
If you measure the spatial distance across the bridge, measure between the two black hole horizons, this distance grows linearly as you move forward in coordinate time. This growth is an invariant physical statement about the interior structure.
So the internal geometry is evolving even while the exterior appears frozen in time. What does this growth imply about the nature of time?
It implies that temporal evolution is fundamentally encoded in the geometry of the connection, the entanglement itself. Time isn't flowing externally. Rather, the geometry that manifests the correlation is evolving internally. The expansion of the ER bridge physically measures the temporal dimension relative to the underlying entanglement structure.
It just reasserts the lesson of the entire deep dive. Time is not an absolute external variable. It is inextricably tied to the relationships, correlations, and dynamic structures that make up the universe. That change, whether it's the spreading of entropy or the growing distance across a wormhole, is time.
That's it.
We began by questioning our most intimate concept, time, and found it to be a phantom. We've seen it dismantled by general relativity, disappearing entirely into the timeless wave functional of the Wheeler-DeWitt equation, and finally recovered as a relational, emergent phenomenon rooted in chaos and correlation.
Time is likely an abstracted phenomenological concept, a narrative we construct from the specific, fixed correlations contained within a fundamentally timeless landscape. Our perception of flow is an extremely powerful illusion.
And the most incredible detail in our sources relates to the origin of this illusion. The existence of a flow of time, the required emergence through the semi-classical approximation, depends on the initial state of the universe being incredibly vanishingly specific.
The estimate for the probability of the initial cosmic state being ordered enough to allow for the observed emergence of time and the era we see today is roughly e to the power of minus 2.9 times 10 to the 122.
That number is so small it is essentially zero.
It's effectively zero. Our sources suggest that if time only emerges from this highly improbable, ridiculously specific quantum origin, perhaps the greatest trick the cosmos ever played was convincing us that yesterday and tomorrow were fundamentally different places.
When in reality, we are simply navigating a predetermined frozen landscape of correlations defined by a vanishingly specific cosmic quantum state.
The good news is that this isn't just philosophy. The hunt for experimental evidence of Planck scale decoherence offers us a concrete path to test the hypothesis of time as an emergent phenomenon rooted in fundamental cosmic chaos. If we find that inherent messiness, we will have verified that the ticking clock we use is just a geometric echo of the universe giving up its perfect order.
What if all time exists now, contained within the correlations of this single, vast quantum snapshot, and our localized consciousness is only capable of perceiving that correlation pathway sequentially? Makes you wonder about the definition of memory and destiny. That's certainly something to ponder the next time you look at your watch.